Hi, my name is Brent West, and I'd like to share with you a presentation that I created for my business school reunion on self-driving cars and the coming robotics revolution, with the hope that it might be interesting to a broader audience. So, in the last few years of my career, I've noticed a major trend happening and something that I feel like isn't broadly understood. So I wanted to share that today, and that is that a robotics revolution is underway. So what is a robot? What am I talking about here? Well, simply I'm talking about machines that can independently sense their environment, make decisions about what to do in that environment, and choose and take an action, all in real time, all without human intervention. And so we see several examples here on the page. The top left, we have Waymo, which is Google's self-driving car. We've got an example from construction here at Komatsu. Top right is a SpaceX example, so aerospace, logistics and packing, farming on the bottom right. But really, across a variety of industries, we're seeing an explosion in innovation and problems that couldn't be solved several years ago, now solvable, and a lot of investment and exciting change on the horizon. So what's happening now that's unique? Why now? Well, this is in some ways an extension of the machine learning revolution that's been going on for several years now. And the way I'd characterize this is we're making a fundamental transition from digital to physical. So we've had machine learning deployed in the digital realm. Google's Translate, I believe, deployed deep learning in 2016. You've had facial recognition, spam filters since I think about 2012. So in the digital world, we've had machine learning make it into products. In the physical world, it's just now become possible. So why is that? Well, there's really three main enablers here. The first is an absolute explosion in the quantity, variety, quality, robustness, cheapness of sensors. So if a machine needs to sense their environment, they have to be able to pull in information about that environment. And the sensors have just gotten so much better. So think about your cell phone camera. I mean, maybe 15 years ago, you didn't even have one, or if you did, it was truly awful. And now, you look at the Apple iPhone billboards, maybe you have the Google Pixel phone. The cameras are quite good. So imagine that same thing happening in terms of an absolute fundamental shift in the quality of output, but happening across a variety of realms, be it radar, LiDAR, which is sort of a way to see how far away a point is in space using a laser, ultrasonics, all kinds of different sensors. So really just a fundamental shift in quality on the sensor side. The second thing is that algorithms have gotten quite a bit better themselves. So here, this is a screen capture of something called AlexNet, won a big image classification contest in 2012, the ImageNet contest, and this was a neural network. So a fundamentally different approach, trounced the competition, really changed the game. So what we're seeing is machine learning algorithms really come into their own, especially as it relates to processing sensor data like camera data. Now, the one downside is these algorithms need a ton of compute power, especially if you want them to run real time. So that brings me to the third leg of the stool. We've got sensors, we've got algorithms, and it's compute. So here is an example from NVIDIA. This is their Drive PX Pegasus computer. This thing's an absolute flamethrower of a computer. I mean, really just tremendous computing power, and it's amazing that it can fit in your trunk, and it's now, being automotive hardened and things like this. So tons of investment in the space. So again, everything a robot would need to sense or see their environment, there's your sensors, decide what it wants to do, there's your algorithms and compute, and then take an action, all in real time. And again, this is something that we just couldn't do 5 years ago. Here's an example from Zoox. This is, I guess it would be an interim output of their self-driving stack. So you've got this video feed in Las Vegas, and you can see that it's seeing objects and classifying them and putting bounding boxes around them in 3 space. So you've got blue boxes around vehicles, you've got purple boxes around pedestrians, and you can see it's doing a good job of marking the objects They're not coming in and out. They're not bouncing up and down in space. Again, this is a demo video, but pretty impressive stuff, and it's not something that was possible even a few years ago. So huge strides, lots of investment been made. Where are we? I would still say we've got a ways to go in solving the technical issues in self-driving. So hard to say exactly how far, but let's just say, if I had to guess, approximately halfway there, let's say. So lots of strides made, lots of ground left to cover. What I do think is interesting is that when I speak to people in the general public, relatives, even people who work in related spaces, oftentimes they overestimate and sometimes dramatically overestimate the current performance of autonomous vehicles. And I think this is understandable for a few reasons. The first is there are folks in the industry who have made some relatively bold promises and haven't always lived up to them. So there's this sort of sales aspect happening here where you, of course, want to put your best foot forward. You're trying to attract investment. You're trying to, in some cases, sell product, and people are promising things. So there's just a fundamental amount of salesmanship happening here, let's say. The second thing I think is a bit more psychological. So it's natural, I think, to see something work once and say, oh, well, it works. You know, you see a car drive over a bridge. You see another car driving at the bridge. You don't think, oh no, they're not going to make it. You just saw a car go over the bridge. It's all fine. You know, of course, the bridge should work. And for many things, that type of logic works. For self-driving, it doesn't really work. You have to think a bit more like a statistician. Well, I saw this 1 mile of driving, but what about the next mile and the next mile? And what are all the little minute details that might be different, that might make the outcome different? And this can be as small as, you know, the angle of the sun in the sky, or a bag that happens to fly across the street, or a cyclist, or just a car of the wrong color. You know, many, many different things can go sideways. So you really want to think like a statistician. It's not just what I saw in a demo, or this one time, or this 5 times, but what's going to happen over millions of miles. And for that, you need a lot of data. So I say here, good enough performance is the bar. What does that mean really? Well, I think it's very likely that self-driving vehicles are going to be comped against human drivers. And I also think it's quite likely that self-driving vehicles will be held to an even higher standard than human drivers. It makes sense. You're giving up control. I want to know that the thing that's driving me around is going to be a superlative driver. So let's see how well humans do today, just to understand the bar. Well, miles per accident, about 200,000 miles per accident, so pretty good. Miles per injury, about 1 injury every 1.5 million vehicle miles, also quite good. Miles per fatality, 1 per 100 million vehicle miles. These are all United States numbers, by the way. To put that in context, that's 1 fatality for every 7,000 years of average working age driving. I mean, that is a lot of driving. So if you came to me and you said, hey, I've got the self-driving software, it meets human performance, I can prove it, I would say, great. You know, I'd still want to see you drive about 300 million miles without fatality and hitting these average injury and accident stats to prove that you're up to human performance level. So the bar is extraordinarily high, and the number of miles you have to drive to prove it is extraordinarily high. So very challenging to meet the bar. Where's all the work going today? Well, the basics are largely covered. So the cars can see the lane lines, the cars can see people generally, they can see the cars. So where's the work going in? Well, it's all about these edge cases. So here's a fun example. This is actually one of the early Google cars. This is actually a Toyota Prius. And what you're seeing here is an older lady in a wheelchair, motorized wheelchair, with a broom chasing a duck around the street. And you might say, I mean, if you sat in a room and tried to come up with the craziest stuff you'd see with one of these cars, I doubt you'd come up with a scenario. And yet here it is, and the car's got to stop. So even when you see very bizarre behavior, you have to behave appropriately. Something a bit closer to home. You might think about Halloween. Well, it's this day of the year where people don't dress like people anymore. That's a problem when you're training a car to look for people. So something to consider. Another classic example here, the traffic cop. So when the light's green, you go. When the light's red, you stop. Unless there's a person standing there who is dressed in a very specific way and moving their arms or legs in a certain way. And then you have to do something different. So how do you identify that person? How do you know what they're trying to tell you to do? You got to behave appropriately, or you could be creating a safety critical situation. So again, very, very tricky. And this is where the investment's going. So how do I know the intent of a pedestrian? How can I tell, a child and what they're going to do and how that's different from, say, somebody on a bicycle who's riding on the sidewalk or something? So it's a very tricky problem. But this is where the investment's going, is really in tamping down that long tail. Just turns out the tail is really, really long. So I've talked a lot about the challenges and why this is so hard and why it requires a lot of investment. But I do want to share my utmost confidence that we will solve this problem. With today's technology, with enough time and resources, we can solve the self-driving problem technically and get one of these vehicles on the road. So we got this. So let's just, for the rest of the talk, assume that the technical issues will get solved. And now let's talk a bit more about the business implications of solving this. Well, the first thing I want to throw out there, and I'd be a lousy product guy if I didn't start with the market, is the market is absolutely huge. So just in the United States, when we look at household spending, we see about $1.2 trillion a year go towards transportation. The vast majority, almost 100% of which, $1.1 trillion, goes to personal vehicles. So that's over 5% of GDP right there. Add in, call it about $800 billion a year for on-road trucking and logistics, and then throw in business fleets, government fleets, corporate spending on taxis, etc. You're easily at $2 trillion a year for on-road transportation in the United States, so about 10% of GDP. To put that in perspective, all digital advertising in 2019 in America was about $125 billion. So nothing to shake a stick at, huge industry there, but 2 trillion, massively, massively bigger. So the prize is just enormous. So what's the model going to look like when we solve this problem? And here, let's compare the per mile cost of three major contenders for car ownership. Individual car ownership as it exists today, without autonomy, ride sharing as it exists today, and then a hypothetical autonomous rideshare offering. So starting on the left with individual car ownership, one way to view your costs is that you're a fleet operator with an N of 1. So compared to the best fleet operators in the world, and I'll call myself out here, me and everybody else I know included, we're relatively unsophisticated at buying cars, selling cars, buying tires, oil change economics, even down to when you have a dent, knowing the right PDR person to call and getting that thing fixed. I mean, there's a whole industry and art around this. And when you're at N1, you really can't tap into it. So your costs are going to be higher. Additionally, you've got some overhead. You might have to pay for city parking, things like this, etc. So this defines your per mile cost, and we'll just tag that at the red line here for the individual. So let's compare that to rideshare economics today. Still generally a fleet of one, so an individual, but you have much higher utilization. So they're driving a lot of miles a year, usually with a car that's designed for rideshare, so or something like it. So a Toyota Prius, for instance, being a very popular car, very efficient, relatively cheap to insure car. You do still see your costs are down there a little bit on per mile for the vehicle itself. Do still have a little overhead, but it's heavily leveraged because of all those miles. And then the big extra cost here is the driver, because you have this extra person in the car, and you also have to pay the rideshare companies on top of it. So by and large, rideshare today, more expensive than owning a car today. It should be intuitive to you. I mean, stats would say almost, the vast majority of people still own cars. It's only in city environments where the fixed cost or the overhead are very high, say for parking, and maybe the mileage per year is very low, that all of a sudden the balance tips towards just getting rid of the car, going rideshare all the time. But should be pretty intuitive. Rideshare today, more of a luxury and for business travel. But let's compare that to a hypothetical future with autonomous ride sharing. And what you see here is a very different picture. So first of all, you're operating a fleet not at the scale of, say, one vehicle, but a scale of more like 100,000 vehicles. So fundamentally, it's a different game, and the costs per mile go way lower. Second, you do have to add in new hardware. So you've got the compute, you've got your sensors to enable autonomy. You do have some variable costs on top. So you might have teleoperations folks who are looking after these cars virtually, support staff if there's a breakdown or you need to unstick something, etc. So there's some costs in there. And then you do still have to pay the rideshare company. But by and large, this is going to be way cheaper than rideshare is today. And we expect it to be, or I expect it to be, I should say, cheaper than owning a car is today in most cases. So what does this mean? Well, it means if you're a rideshare company today, autonomy is an existential threat. So if you're wondering why Uber, Lyft, others who are in the rideshare space are so concerned about autonomy, it is exactly for this reason. They simply cannot compete with a hypothetical autonomous rideshare provider. They'd be out of business. So it's extremely important that they have an answer here, either through partnerships or having the technology themselves. It's also worth noting that I would expect individual car ownership to decline over time and potentially relatively rapidly and move towards rideshare. So here I've called out the per mile cost. It would be cheaper to have a rideshare car than to own a car, but this doesn't even account for several other factors like the pure convenience of having an autonomous rideshare car. I can take the train to work, say it starts to rain or something, I can take an autonomous rideshare car home. I didn't have to have my own car there. That's pretty nice. We're not including the time it takes for you to sit at a Jiffy Lube and wait for an oil change, or the work you have to put in to wash your car. Now, there are some countervailing factors here, like the pride of car ownership, etc. But net, I would expect to see people over time get rid of this asset and embrace autonomous ride sharing. Worth noting too, ride sharing has some unique network effects and economics here. So basically you've got this wheel where when you have, say, let's start on the top, more riders interested in your service, it allows you, so that's more demand, it allows you to add more supply, in this case, autonomous vehicles. Now this means that you have better unit economics on your fleet. It also means that you can offer a better rideshare service. So I have more vehicles. That means the wait times are lower because there's more density of cars available. It means that there's just generally more cars available, so you're less likely to have sort of no service available, etc., say at a remote airport or something. It also lowers that per ride cost. So I've got a better service, I've got lower cost. What does that mean? It means more people interested. It means more riders. So more riders or demand begets more supply, begets more riders, etc. And so I'd expect to see fewer bigger survivors in the on-road autonomy race. And I'd specifically expect to see that as we converge on ride sharing as an answer. So if you think about all the rideshare companies today, the tech companies chasing the prize, the OEMs who currently make cars, and you think about how many slots there are in the future in those ride sharing call it company jobs, or just like chairs, if you will. There aren't that many chairs. So it's going to be interesting to see what happens, but it's a bit of a race. So I talked about rideshare and why this is an existential threat to the rideshare companies that exist today. Let me talk a bit about OEMs. OEM meaning a company like Ford or Tesla or Toyota, etc. So what does rideshare future mean for them? Well, it means, let's say that you don't have an autonomy offering, that you're an OEM, and ride sharing is taking off as the predominant business model. Well, it means that far fewer cars or vehicles are going to be purchased than today because those vehicles can be leveraged much more highly in the future. They just each drive many more miles. You're not selling to consumers anymore. Generally, you're going to be selling to one of a relatively small number of business customers, these rideshare companies. So you've got a lot of power and concentration in those customers. And then this isn't really an environment where you're going to be able to differentiate on your brand, off the features of your vehicle. I would expect this is going to be an RFP, build to spec type situation where the vehicle is defined by those rideshare companies. So all in all, all these dynamics point to a lower volume commodity, I call it here people pod, but you're really just building the vehicle to spec. There's going to be a lot of competition for these relatively few slots of producing these vehicles. And again, if you think about the OEM industry today, there just aren't going to be enough chairs left. So not all the current players will survive in this future. I would also expect us generally to see the value in the value chain flow to whoever can provide the autonomy solution, owns that technology. So value in the value chain, it's just a fancy way of saying the people who own that technology are going to make the most money and be in the most advantageous position. Okay, so look, if we want to simplify the world here, we got two classes of groups going for this here. We got tech companies on one side, the Waymos of the world, Apple's in there, even though sometimes they act like they're not in there. They're totally in there. They're going for this. You've got Uber. So you've got these tech companies on one hand, and then you've got the OEMs on the other hand. And I'm going to put Tesla in that bin because the way they're attacking the problem is more like an OEM, but and their dynamics were more like an OEM, which we'll talk about, even though they have incredible engineers and technology. But you also have Toyota, Ford, GM on the other side. So you got these two groups. I'm not going to spend much time talking about the advantages of the tech companies. They're pretty self-evident. I mean, they have tremendous engineers, they have tremendous resources, huge fat cash flow that they can divert from, say, online ads to try to solve self-driving, in the case of, say, Google or Waymo. And they got a lot of advantages. But I think OEMs have two very distinct advantages, which I do want to talk about because they're maybe not as intuitive. The first advantage here is that OEMs get to monetize the journey, or they can make money as they develop this technology. So what do I mean by that? Well, let's look at these SAE automation levels. You may have heard of L1 or L3 or L5 driving. Basically what this says is, okay, L0 is nothing. Let's ignore that. That's just a human-driven car. Well, L1, L2, even L3, this is an idea that you're adding in features like lane keeping assist to keep the car in the lane, electronic braking assist. If, say, a vehicle, if a collision is imminent and you aren't braking hard enough, it's going to help you out. Or sometimes if you aren't braking at all, it's going to brake for you. So great features, but fundamentally driver assist features where you're liable and still driving the car. And then L4 is essentially that it's a full self-driving car, but only in certain domains. So, but this can be pretty broad. So maybe it's like, hey, when it's daylight, or anytime except for when it's, a haboob in Phoenix or something. And then L5 is full autonomy, which means it can drive anywhere all the time, just like you can. So really the prize is getting to L4 plus. So again, what's the big difference here? Well, if you're Waymo, you really don't have a business until you get to L4, at least. What do I mean by that? Well, you got this massively expensive self-driving car. Got cheaper over time, but right now it's massively expensive. And until you get to L4 in performance and safety, you got to have a safety driver there in that car. So you have all the cost of the manned rideshare, plus all the technology cost of the autonomous rideshare. Not economical. So yes, you can run a service. You could even sell many rides at scale, but you're going to be losing money on every single one of those rides. So for the tech companies, including Waymo, but this is all of them, Uber, etc., from a self-driving standpoint, it's all about getting to L4 as quickly as possible. So this is why you see, like in the case of Waymo, them going for one of the easier domains. So it's either Chandler or Candler, and I can never remember how you say it, in Arizona. Relatively simple environment, good weather. They're trying to solve it there, copy paste that other places, and then expand. It's all about the domain, solving one domain. OEMs, so they make money all the way there. So, okay, great. I create lane keeping assist. I can sell that to customers. I create electronic braking assist. I can sell it to customers. Your Tesla, and now your autopilot works on 2-lane roads. Well, great. That increases willingness to pay. So every little feature they add, they get to charge customers more and delight customers more. So fundamentally different dynamic here. I would add too that as the race drags on, and we'll talk a bit about that in a minute, but as the race drags on, being in a position where you can monetize the journey is, I think, going to be important. Here's another OEM benefit that, again, it may not be as intuitive, which is that not only do you get customers to pay for your technology, you also can use them to lower your development costs. So let's, again, use a Tesla example here. Let's actually talk about this wheel for a second before I get into what Tesla's doing with it. This is sort of the classic machine learning product development cycle. And it's very different than developing a normal product, normal technology product, I guess I'd say. In that, let's say I want to make a new website to sell shoes, and I'm not going to be selling 5 billion shoes a year. I'm just going to sell a relatively modest amount of shoes. So no major unsolved technical problems here. I just want to sell shoes on a website. Well, I can spec that out. I can figure out how much the features I want, how long it'd take to make each one, the time and the cost. You can even like Gantt chart the whole thing out if you want to and make your website, and you're going to be pretty close. But you want to solve a major unsolved machine learning problem, you're in a totally different ballpark. So, you're in your planning meeting, you talk to your engineers, and you want to know, okay, guys, like, what kind of sensors do we need? What kind of camera do we want? I don't know. Okay, well, how big a compute do we want? Like, what kind of compute do we need? I don't know. What's the power budget going to be? I don't know. Nobody knows. I mean, it's never been solved before. And so what you got to do is you come up with, we'll start at the top, you come up with a hypothesis. So I don't know, let's say I want to see cars on the road. Well, let's say I want to use a monocolor camera to do that. Great. That's my hypothesis. I can see them with a monocolor camera. Well, I'm going to pick the camera. I'm going to pick the architecture. So I'm going to put it on my car, wherever I think it should go. I'm going to take that car out. I'm going to drive it around, collect some data with that camera. I take it back. I do something called data labeling, which means that I essentially take those images of cars that came from my camera, and I'm going to go either draw boxes around the cars or go pixel by pixel and draw essentially in the car. But I'm creating this ground truth of this is car, this is not car, this is lane line, this is not, this is free space, pedestrian, whatever. And then once I have those labeled images, I can train a model off them. So I can feed them into a neural network and kind of like cycle them through and learn what's a car and what's not. So I can use those images that are already labeled. I can actually use those to evaluate performance as well, but it would be even better if I could do that in the real world. But anyways, this is your basic wheel. So you have a hypothesis, you do data collection, you label that data, you train a model, you evaluate the performance, and then you go back and tweak your hypothesis. And that might mean new sensor, it might mean more data, it might mean different network, whatever. But to win, the idea is you want to get around this wheel as quickly as possible, as cheaply as possible, and keep hitting it and learning and learning and learning. It's all about learning. And one of the most expensive things in here is the data collection. For folks that are new to machine learning products, it's one of the things that oftentimes surprises them, let's say, is the importance of data collection and that function and the cost of it. So very different than a normal product. So anyways, this is your machine learning wheel. Let's see what a great OEM here, Tesla, is doing to lower their development costs. Well, first, like we alluded to on the last page, They set their system architecture, which in this case was a series of cameras on the car, and then they got customers to pay for it. So quite clever and good on you, Tesla, there. So looking good so far. So not only did customers pay for the sensors as a feature, but they also bought the car. And then what do you want to do with the car? Well, you want to drive it. So those miles those customers were driving, the whole time Tesla's able to pull data and sample images from what's going on out there. So they get that data for free. They also can upload it over your home Wi-Fi when you get home. Also free for them, so pretty good. So they do have to, also worth calling out, the tremendous variety they get because of the number of vehicles out there and the total aggregate mileage being driven, again, which they also don't have to pay for. Very, very nice. They do have to label the data and train models. I mean, that's just sort of everybody has to pay for that. Performance evaluation, they've got a really interesting option here, which is that they can run the models in the background while you drive, compare the output, so what the model did to what you did as the driver, and when there's a disconnect, make sure that they're flagging that as an opportunity for learning. Really, really, really interesting thing that they're doing there, and solves an important problem, which it gets down to data quantity and management. They could, in theory, pull all this data in from the cars and do the same kind of assessment remotely. It would just require a massive amount of data to be transferred and stored and handled. Doing it locally saves them that hassle. For the icing on the cake here, since these are driver assist systems, unless there's just tremendous negligence on their part, you, the owner and driver of the car, are liable for any issues that might occur. So they also get to offboard that on the consumer. So looking at this, I mean, it is a really, really clever strategy here. I got to hand it to them. It's quite good. So I would imagine that other OEMs and tier ones will attempt to replicate this ecosystem, but as far as I can tell from the outside, no one's doing it quite like Tesla is. So we mentioned OEM, we mentioned tech plays. Let's go back to those tech plays for a second. Worth noting, amongst the OEMs, I believe Tesla is in the lead. So amongst the pure tech plays, who is in the lead? I would argue Waymo's the clear leader. They've been at it for a long time. They got a really solid team. They've invested a lot of money, but it does come at a price. So they're probably spending close to about $1 billion a year right now. Again, you look at the price, you say, hey, US only, $2 trillion plus a year top line, huge prize. $1 billion a year doesn't seem that big, but even pre-coronavirus, I would say the amount of time it's taken and may take would test even the most patient board and corporate leadership. And I think in a risk-off, more conservative environment like we're entering right now, it will test their mettle. We'll see if they can stick at it with that level of investment, though I'd argue the prize is there. And so because of this dynamic of taking maybe a bit longer than folks expected, even relatively savvy individuals, as well as just the general business environment as of June 2020, I'd expect to see a wave of consolidation. So acquisitions, maybe some consortiums coming around, and just good old-fashioned failures. If you're a startup, you got to have a really good story for why you can credibly beat Waymo at this game. And it's really hard to tell that story. I don't know that it really holds water. I mean, again, demos are great. They might sell, they might get you a Series A. I don't even know if you can get funded anymore in this type of space. It's just so late. But you got to have a great story. And in some ways, you're almost only viable strategy at this point, if you're relatively early on, is to get, you're hoping for an acquisition essentially. So expect to see fewer players here over time. But hey, these guys have the benefit of being relatively uncluttered. They don't have to monetize the journey. And in the case of, say, a Waymo, they have access to tremendous amounts of capital. So, they get to focus on the prize and go right for it. We'll see what happens. So when will this tech be ready? Many caveats here. First of all, this is highly speculative. Every player is very secretive about their real performance. So I can only guess. But my best guess is that we're still 5 to 10 years out from being technically able to have what I'd call a no caveats at scale launch. So what does that mean? It means getting at least 10,000 vehicles out there in fleet, ideally 100,000. No safety driver in those vehicles, driving all times of day and all weather conditions in both highway and surface street driving, because you could make a highway only service. It is slightly easier, but if we're really talking the whole thing, you'd have to do both. The scale does matter because with a small fleet, say 5 cars, you could ship this thing and not quite be hitting that human safety level. You would be running more risk per mile, but you're doing so few miles, you might just get away with it. To me, then it's all when you're if you really have it, you're going to show it with the scale. And so I'm looking for at least 10,000 cars. X factor here is Waymo. They've invested a lot of money in simulation. That could pay off and lead to some nonlinear jump for them. So they might pull it off in the next 5 years, but I still doubt it. I'd say 5 to 10 for the technical problem to get solved. Do also have to call out that solving the technical problem is not enough. There's still a question of legal and regulatory issues. There's still a question of liability and tort issues. When there's an issue, is the liability unbounded or not? There's just a societal acceptance question. What's the performance need to be? When there are accidents, which are inevitable, how does society react? Do they want these things banned or not? And then there's also the reality that certain industries and jobs will be affected by this technology. And it may be that for very legitimate reasons, regulators want to slow the advance of this technology to provide more time for folks to, say, find employment in another industry than, say, Class 8 trucking or something. So not just about the technical hurdles, also have to solve the business hurdles and regulatory hurdles and other things. But 5 to 10 years, definitely possible. So we started this talk by mentioning the robotics revolution and many applications, but then we talked a lot about self-driving. So I want to place self-driving in a space of attractiveness for you. And so being a reformed consultant, I had to throw in a 2x2 matrix. And in a 2x2 matrix, you always want to be in the upper right-hand corner. So let's set the axes to make that so. So here we've got the value of the solution, low on the bottom, high on the top. And then we've got the cost to develop the solution, high cost on the left, low cost on the right. So again, you'd want to be in the upper right. So high value solution, low cost to develop. Let's see where self-driving winds up on this page. About as high in value and high in cost as you could possibly imagine. It is the upper left-hand corner of the upper left-hand box. So probably not when you're talking about a technology shift, and this robotics revolution and all these things that are solvable today that weren't solvable before, not really where you'd think you'd start. And it begs the question, what about all this stuff? What about the low cost, high value stuff? Well, let's get into the weeds for a second. And I mean that literally as an example. So this is an example from farming at Blue River, where I currently work. It's a subsidiary of John Deere. And there's a product under development there called See and Spray. And See and Spray is deceptively simple. You have a sprayer that goes across a field, and you have cameras that look down. And for every camera, you basically look at every pixel it sees, and you classify that pixel into one of 3 things. It's either a weed, it's a crop, or it's dirt. That's it. And then you spray the weeds only, and you move on. That's the whole product. This thing is an absolute amazing product. At least a $30 billion a year opportunity, leads to 90%, up to 90% herbicide savings. So great for the environment and great for John Deere, the corporate parent. So good for customers, good for business, good for the environment, just a dynamite solution. And again, deceptively simple. Certainly belongs in the upper right-hand corner of that relatively low cost, relatively high value trade. So what might be the See and Spray? What might be these killer applications in your industry? Well, really, I can't tell you because you need two things, and I only have what's on the right side of the page. The first thing you got to have is deep knowledge of the industry and deep knowledge of the customer and their problems and the economics to really understand where the value is or could be and what the future with the technology could look like. I'll tell you what, you get the best computer scientists in the world, you get the best machine learning folks in the world. You don't pair them with a farmer or an agronomist, they're never going to come up with See and Spray. It's just too far afield. They have no idea anything about that world. So you got to bring in the industry expertise. But you also need a clear vision of what's possible with the technology today. And so you need to bring that lens in as well. And so the intersection of those two things, that's where you're going to find your killer applications. Well, in closing here, I have to throw in, I feel like, a sports analogy. I know a lot of folks love sports, and it seems like everybody loves Steve Jobs. So I'm going to combine them here for you in one quote, which is Steve Jobs reading a Wayne Gretzky, the hockey great quote: "I skate to where the puck is going to be, not where it has been." And not to put too fine a point on it, but this is where the puck is going. This fundamental technological shift that allows real-world robotics problems to be solved in a way that just wasn't solvable a few years ago. This is very exciting. It is happening right now. And I would think about what this means for you. So if you work in an industry where one of these solutions might be viable, be thinking about whether or not you have a good answer, whether you have a good solution in process yourself. If you're an investor, think about your portfolio companies and ideally be investing in the leaders in the space. If you're an entrepreneur, well, you know what to do. There are huge opportunities out there. Again, very, very exciting times. And I just want to say thank you again. It's been a pleasure to share some of the learnings I've had from the last few years. And, feel free to reach out to me on LinkedIn. I love jamming on these topics and would love to meet some of you. So thank you again.